गुड मॉर्निंग टू एवरीबॉडी। आज हम MSc फिजिक्स में सेमेस्टर फर्स्ट में क्लासिकल इलेक्ट्रोडायनेमिक्स में यूनिट फर्स्ट का एक इम्पॉर्टेंट टॉपिक डिस्कस कर रहे हैं एंड दैट इज ग्रीन्स थ्योरम। ग्रीन थ्योरम क्या है, किस तरह से इसका डेरिवेशन होता है, इसकी ज़रूरत क्यों है, वाई वी नीड द ग्रीन थ्योरम। So, as per we know, in electrostatic problems, if there is no boundary conditions and the charge distribution is the discrete or the continuous, then to calculate the potential, we can use the simple formula, the phi equal to 1 by 4 pi epsilon naught integration of the rho x dash dv divided by x minus x dash, where source is in form of the volume charge distribution at x dash and the observation point at x. So, if we have some boundary condition, then this formula cannot be used indirectly. So, we have to use an alternate method and that is given by the Green's and called Green's theorem. Now, the Green have given the many identities. Out of these, the two important identities that is also known as the theorems of the Green's or the derivations of the Green identity. Green's first identity. Using simple Gauss divergence theorem, we can write the volume integration of the del of the A is equal to the surface integral of the A with respect to the surface dA. Let us consider A equal to the phi del psi, where phi and psi are the two arbitrary scalar functions or the fields. On substituting this value, we obtain the left hand side of this Gauss divergence theorem, that del of the phi of the del psi of the dV equal to del phi del psi dV plus phi del square psi dV. And for right hand side, can write the integration surface integral for the closed loop for the A of the n cap dA. In place of the A, I have write the phi del psi, then this will be converted into the phi del psi n cap dA. Here phi del psi को हम लिख सकते हैं phi del psi by del n, because this is in along the n cap that is perpendicular to the surface direction. So, we can write right hand side is the surface integral for the closed loop phi del psi by del n dA, and here we have used del of the phi del psi equal to phi del square psi plus del phi del psi, and the phi del psi dot n cap equal to the phi del psi by del n. Here del by del n is the normal derivative at surface directed outward from the closed surface. Equation 2 and 3 can be combined and we obtain the del of the del phi del psi dV equal to the del of the del phi n cap dA, and this gives the important first identity, that is the phi del square psi plus the del psi del phi dV equal to the closed loop integration for the surface, that is the phi del psi by del n dA. This is known as the Green's first identity. Now, to obtain the second Green's identity or Green theorem, we have to use the first identity as well as the another equations in which phi and psi are interchanged. So, by interchanging the phi to psi, we get A vector equal to the psi del phi, and the volume integration of the psi del square phi plus del phi del psi dV equal to the volume surface integration of the psi del phi by del n dA. On differentiating equation 5 from the equation 4, we get del phi del square psi minus psi del square phi of the dV equal to the psi for the closed, that is the phi del psi by del n minus psi del phi del n dA. This is also known as the Green theorems or the Green's second identity. What is the use of it? This theorem is used to solve the electrostatic problems with the boundary conditions. Now, applications of Green theorems. It gives the relation between the integral and the differential form of the Maxwell equation and the energy of the steady currents. And second, Poisson differential equation for the potential we can write, and using this one we can obtain the many different types of the Green theorems. So we know the Poisson differential equation, del square phi equal to minus rho by the epsilon naught, where rho is surface volume charge density. So change this equation into the integral form, we have to change the psi equal to 1 by r, 1 divided by x minus x dash, where x is the observer point and the x dash is the source point, and the phi is replaced by the scalar potential, that is the phi. So we know very well that del square of the 1 divided by x minus x dash, or the del square by 1 by r equal to minus 4 pi del of x minus x dash, where the del x minus x dash is the Dirac delta functions. So in Green theorem, we have to substitute this value psi and phi and use the del square formula. We obtain what is the Green theorems. Phi del square psi minus psi del square phi volume integration equal to the surface integration of the phi del psi by del n minus the psi del phi by del n. Here the psi equal to 1 by r equal to 1 divided by x minus x dash, and the phi equal to the phi. So phi del square 1 by r minus 1 by r del square phi volume integration equal to the surface integral of the phi del by del n 1 by r minus 1 by r del phi by del n dA. And we have given that del square phi equal to minus rho by epsilon naught, del square 1 by r equal to minus 4 pi del x minus x dash. So substituting these values, we obtain minus 4 pi x dash del of the x minus x dash plus rho x dash by the epsilon 0 r volume integration equal to surface integral of the phi del of the del n 1 by r minus 1 by r del phi by del n dA. And using this formula, minus 4 pi integration phi x dash del by del x equal to minus 4 pi x. So this gives the potential minus 4 pi del phi plus rho x dash by the dV epsilon naught r equal to the minus phi 1 by r del phi by del n dA plus del phi del by del n 1 by r dA. And on calculating and substituting these values, we obtain the phi x equal to 1 by 4 pi epsilon naught rho x dash dV by the r1 plus 1 by 4 pi integration volume surface integral 1 by r del phi by del n minus the phi del phi del n 1 by r dA. This gives the three terms in the right hand side of this one, means the potential is the combination of the three terms. The first term, what is the physical interpretation of these three terms? Physical interpretation of the first term represent the potential due to the volume charge distribution inside the given volume, 1 by 4 pi epsilon naught rho x dash dV x minus x dash. The second term of the right hand side, 1 by 4 pi epsilon naught 1 by r epsilon naught del phi by del n gives, due to the surface charge density sigma epsilon naught del phi by del n. And the third terms on the right hand sides gives 1 by 4 pi epsilon naught minus epsilon naught phi del by del n 1 by r dA due to the dipole layer density. We know that capital D equal to minus epsilon naught phi. So this gives the potential due to the dipole layer density. So according to the boundary condition, above three terms gives their contributions. If the surface S goes to the infinity, then the second term and third terms will be equal to 0. Only point charge potential will be there. So this is sufficient for today. Thank you.